Hi, I'm Dr. Incognito. In this video, we're going to study the root test. The root test goes like this. Suppose we're given a series, summation an. We're going to consider the limit as n goes to infinity of the nth root of a sub n. Call that limit L. Then if L is less than 1, the series that we were given converges absolutely. If L is greater than 1, the series diverges, and if L equals 1, then no conclusion. So let's take a look at an example and see how this works. Let's look at the summation n equals 1 to infinity of n squared plus 1 over 3n squared plus 2n to the power 3n. Now the idea of the root test is we're taking a series that has a geometric property to it, but it's not exactly geometric. See, the nth root of the nth term of a geometric series will converge to the common ratio of the geometric series. So if we look at this one, it's not a geometric series. We have this complicated fraction here raised to the power 3n. But let's look at what's happening if n is large. If n is large, the fraction in the parentheses is headed towards 1/3. And if we look at the summation of 1/3 to the 3n, that is a geometric series. That's the summation of 1/27 to the n. So this is basically behaving like a geometric series with common ratio 1/27. When we take this limit, we will get 1/27. And a geometric series with ratio 1/27, common ratio 1/27, will converge. So the series will converge. In fact, it will converge absolutely, because if the ratio here was negative 1/27, the geometric series would also converge. So let's look at the details of this example. The limit as n goes to infinity of the nth root of the absolute value of an. In this example, we have the nth root of, our fractions are positive, so I'll drop the absolute value, n squared plus 1 over 3n squared plus 2n to the power 3n. And now the nth root and the nth power will cancel. This is going to give me the limit as n goes to infinity of the fraction cubed. So that's n squared plus 1 over 3n squared plus 2n quantity cubed. Let's take a closer look at that. If we have any number x and we take the nth root of x to the power 3n, that's the same as x to the power 3n over n, converting this into a rational exponent, and that of course is x cubed. So you can see the nth power and the nth root canceling, but leaving us still with the third power. And now, as mentioned earlier, the fraction in the parentheses goes to 1/3. We have the same degree polynomial in the numerator and denominator. They're both degree 2. And the ratio of the lead coefficients is 1/3. So the limit is going to be 1/3 cubed, which is 1/27. So this series is behaving like a geometric series with ratio 1/27. And so since 1/27 is less than 1, the series converges. Now, if L is equal to 1, we'll get no conclusion. And to give an example of that, if you take any p series, the summation of 1/n to the p, where p is some positive power, and if we try the root test, the limit as n goes to infinity of the nth root of 1/n to the p. This is the limit as n goes to infinity of 1 over the nth root of n to the p. Here, this limit will be 1. The nth root of n to the p will go to 1 as n goes to infinity. So this is an important limit. More specifically, the nth root of n goes to 1 as n goes to infinity. To prove this, we would use L'Hopital's rule. So I won't go through the details here, but that's an important limit. And putting a power here doesn't change the value, because the nth root of n to the p could be rewritten as the nth root of n quantity to the p. And if the nth root of n is going to 1, 1 to the p is 1. So our limit here is 1 over 1, which is 1, so we get no conclusion. And of course, sometimes the p-series converges if p is bigger than 1, and sometimes the p-series diverges if p is less than or equal to 1. So it's good that we get no general conclusion about p-series, since either possibility can be a reality. But nonetheless, this is still an important limit in the root test, because there are some examples where you might have an n to the p in the problem along with other things. And so when you take the nth root of the n to the p, you'll want to say that the limit is 1 so that you can use the root test effectively. Such an example would be something like this. Suppose we had the summation of n squared over the natural log of n raised to the n. So here the nth power, let's say that we start with n equals 2. The log of 1 is 0. So let's start with n equals 2. We have the nth power here, so we'll try the root test. The limit as n goes to infinity of the nth root of our absolute value of an is the limit as n goes to infinity of the nth root of, our fractions are positive again, n squared over log n to the n. And we'll break this nth root up. It's the nth root of n squared on the top. And the nth root of log n to the n is just log n on the bottom. And that's the point of trying the root test here, because the nth root of the nth power will cancel. And now in taking the limit, the numerator here, that's going to go to 1. And the denominator is going to infinity. So really, this is equal to 0. The limit is equal to 0. And the conclusion then is, since 0 is less than 1, the series here converges by the root test. Okay, so there is a look at